Welcome back to our series on applied regression analysis. I'm Mark Ledbetter. This is lecture video 35. We're in chapter 14, part 2. Last time we looked at some simple approaches to diagnostics, and we saw that it was very difficult to try to find anything wrong, and it's very tedious and time-consuming, and I would suggest that you do not use those methods. I consider them as a waste of time because what we're going to go over now is much better at detecting issues with the data or the model than those simple approaches we talked about last time. But they do give you the perspective of people who might use them, and maybe if you're in a professional setting, you can gently move them towards the more robust methods that we're going to cover here in the rest of the chapter. So we're going to talk about residual analysis, and we have several methods of detecting outliers that we're going to discuss. So let's get started. Before we get started, though, with that, I need to go over some basic matrix algebra and notation so that one of these estimators, the hat, what do we call it? The hat leverages, matrix leverages, I want you to at least know where it's coming from and have some general idea of that. Plus, it is good for you to have a general knowledge of the matrix notation for regression because it's very commonly used, and many people, especially statisticians, they mostly use the matrix notation. So I don't want you to be unaware of it. All right, so we have, now we're going to look at an individual observation. So yi is one of our individual observations. We have n observations in our sample, and so for yi we can write the equation beta naught plus beta 1 xi. Now this is the simple regression model from chapter 5 with only one predictor variable in it, and epsilon I is the error of that ith observation. And so we could write this model for each of the n observations. And we would have something like this, and we want to express this more simply and be able to do some calculations and manipulations and solve things. And it's very difficult to do this as a system of equations. If you remember that from algebra, working with a system of equations is very tedious. If you then worked with matrices, you saw how much easier it is to use matrices and how much less confusing it looks to do so. And so we're going to write y as a matrix, but in this case it's a vector. A vector is a special subset of matrix that has one column. And so we could write the dimension of this matrix as n by 1. Okay, so there's n rows by one column. And that's for y. And then for x, we might have something that surprises you a little bit, but we'll see why this is true. This is going to be n by 2. This is going to be 2 by 1, and this is going to be n by 1 again. And we need these to be put together in such a way that we end up with our original equations here. So we can do that with y equals x beta plus epsilon. And the order here is important. You cannot switch these. Okay? You actually can't multiply them in the reverse order. Matrices, unless they're square matrices, you can't reverse the order. And if you do reverse the order, you may not get the same answer depending on the structure of your matrices. So the order is important in the multiplication here. So let's do this. So I'm going to write y1, y2, y3, or actually I'm going to get rid of 3 and just go all the way down to n. Yn is equal to, now I have x1, x1, 1, x2, 1, xn, and then times beta, which is beta naught, beta 1, plus epsilon 1, epsilon 2, down to epsilon n. Okay. So this is equal to, I'm going to do matrix multiplication, we take each row and multiply it by each column. There's only one column in this one, so we're going to multiply each row by this. So we take the first element here and multiply it with the first element, the second element with the second element. Oh, you can't see that. Let me change color. so that maybe we can see a little bit. So number 1 is going to be multiplied by number 1. And then number 2 here will get multiplied by this, and we add those two together. So what we end up with is beta naught plus beta 1 x. And then we do the second row, and we multiply it by every row in this matrix, or column in this matrix, but there's only one column. So we get beta naught plus beta 2 x, 2, this was x1. And we do the nth row, and we get beta naught plus beta 1. This is not beta 2, this is beta 1. Sorry, beta 1 x3. And then we have plus epsilon 1, epsilon 2 down to epsilon n. And when we do matrix addition, in this case we have the same we have the same number of rows, so we can add them together. So we add this with its corresponding element here, and we end up with beta naught plus beta 1 x1 plus epsilon 1, beta naught plus beta 1 x2 plus epsilon 2, all the way down to beta naught plus beta 1 xn plus epsilon n. And that is exactly what we started out with here. So that is why this notation here works, and I hope you now understand that this row, this column, of 1s is to return the beta naught by itself. Okay? So all the beta, except for beta naught, all the other betas go with a variable, especially in multiple regression. So this is just a basic form here so you can see. Okay, so that's why we have this matrix notation. It does make it easier to work with, especially with the individual elements like betas and x's and what have you. So the least squares is yi minus y hat squared, and we sum all of those squares. And if we substitute in for yi hat in this case, then we end up with this expression. And of course, don't forget the square. And we can minimize this using calculus. Of course, you don't have to know calculus for this class, so we won't do this. But you can differentiate q first with respect to beta, set that equal to 0, and then separately differentiate it with respect to beta 1, set that equal to 0, solve for beta naught and beta 1, and you get your estimates, beta hat. And so if we look at this in matrix notation, beta hat is our estimate of the betas, and it can be written as this, first time I saw it, pretty daunting looking matrix. So we have x prime, which is just the transpose of x, times x, that's too messy, that quantity inverse, and then times x prime of y times y. Okay. Now, if I take this quantity here and multiply, so I take actually this quantity, where do I start? So if I take this quantity here and multiply it by beta hat, then I end up getting this quantity here. So let's look at why we get that just briefly. X prime x inverse x prime x, and then beta hat, I'm going to substitute in for beta hat here. So that's this. And so I have, and I can put a parenthesis around those two, I don't have to, but then I have x prime x inverse x prime y. And so I can either group these or I could group these two, and what's happening is I'll do these, it doesn't matter, end up with the same answer. This, I can think of this matrix, I can think of the first matrix here, and that is the inverse of this matrix, or this matrix, the second one is the inverse of the first one. When I take a matrix times its inverse, I get the identity. okay, which is like 1. But in this case, it's going to be 1s along the diagonal and 0s everywhere else. Oh, and I didn't write that very well, but so then I'd have 0, 1, 0, and then dot, dot, dot along the diagonals, and then I have 0s everywhere else. And it's really hard to draw this matrix when you haven't practiced it in a while. Okay, so this is like the identity, it's like 1. If I multiply that by another matrix, I get so A times I is just equal to A. And I has to be in a certain, or I times A. So one of the two. So they should, if it's a square matrix, they're both the same. If A is not a square matrix, then you can only do this in one side of this. You can't do both if A is not square. Okay? So that's just a property of matrices that, in fact, when we look at this here, I think I said that you can't do beta times x. That doesn't work. The dimensions have to be correct. In this case, I have n times 2, n by 2, and this is 2 by 1. And so I can take an n by 2 times a 2 by 1. These two numbers have to be the same in order for me to multiply them. So I can't switch this because 2 by 1 times n by 2 doesn't work because these are not the same. They have to be the same dimension, and that goes back to the way we do matrix multiplication. Okay, so I is like an identity, and so what happens is I can basically cancel these two out. And so I end up with x prime, x inverse, x prime, y. Okay? Because those two cancel, because this is like, I can say that is A, and this is A inverse, and I can, if A has an inverse, it has to be a square matrix. So if A is a square matrix, it can have an inverse. It doesn't have to. Depends on, it may not be able to, but square matrices are the only ones that can really have a regular inverse. And when you take a matrix times its inverse, you get back the identity. And so that's how we get to this quantity here. And it says, so we're going to see a little repeat because I took these from two different lectures. So we're letting, again, we've seen this, and y hat now, instead of y, we have y hat. So I guess it's different. It is different. So we have the hats now, which we didn't have earlier. And so now we're letting y be this vector of y, or y hat be the vector of y I hats, if you will. And so we have the same expression, except now we don't have epsilon. When we have a hat, an estimate, the e, or the epsilon, goes away because it's incorporated into this estimate. We've incorporated the error into that estimate. Okay, so we don't need to specify it separately. It's already part of those values. So then we're saying that this is possible again because we take these two matrices, we multiply them, and they give us back what we're looking for. So y hat is x beta hat, okay? And as we can see here, so it's x beta hat, and we substitute in for beta hat, and we just simply call this matrix the hat matrix. Okay, so H is the hat matrix here. I'm not going to make you do anything with this hat matrix. It has this important property where when it multiplies by itself, it gives back itself. So that's called an idempotent property. So I never have a good way of saying that word. I always get it mixed up. But they're idempotent, and so that's a special class of matrices which is really nice and makes some solutions very simple compared to what they would be. All right. So let's get into our actual detecting of outliers. And so, okay. So we have this. Okay, I just want to make sure that we have everything we need. And so, again, what we just defined was the hat matrix. And now we're expanding X so that X has more than just one variable. Okay, so we still have to keep this column of ones for the beta knots, right? For the beta zeros or beta knots. And then we have now the first index here is the row. Okay, so that's the observation. The second index, you notice it stays the same. The 1 stays the same because that's basically x1, but now x1 for observation 1, x2 for observation 1 of the second, so it's x1 of the second observation, x1 of the nth observation. And then we have k variables. So you'll notice that the second one, so we go 1, we'd have x1, 2 here, and it would go on until x1k. And this would be x22 on until there, and this would be xn2. And so I hope you see the pattern there. So then the vector of estimated responses is still able to be written. Look how simple it's still able to be written. It's just that x now is very complicated. And beta, if I do beta, not beta hats, then I'd have beta naught, beta 1, down to beta k. All right, so I have k plus 1, so this would be a k plus 1 by 1 vector. Okay, and so then we're going to look at the vector of the residuals, epsilon hat, which is y minus y hat. And so y minus, and see why we call this the hat matrix. Because now instead of saying hat, I put h here and times y. And so I end up with hy, and hy is the hat of y, if you will. The hat matrix times y. So y hat. And I can use, I can factor out y out of both of these, but since y is multiplied on the right of h, I have to factor this out to the right. I can't do it to the left. That doesn't work because that would give me back y times h, and y may not, and you can't multiply y times h. You might be able to, but it'd be a special case, just happenstance. If you have the same number of, you'd have to have the same number of independent variables as you do observations, and that wouldn't be a good model. We'll think about the degrees of freedom. We wouldn't have enough. Okay, so we call it the variance-covariance matrix of epsilon. Why? Because it has both the variance and the covariance in there. So what I'm saying is that there would be sigma squared 1, 1, and then there would be sigma 1, 2, which is the covariance, sigma 1, 3, all the way over to sigma 1k. Okay? And so these are all covariances, and the variances are on the diagonal, the 2, 2. So the variances, this would be, let's see, n, k. All right, n. Oh yeah, I'm sorry. So this would be not k. This would be n. 1n. This would be, well, actually k. I need to use k's. This would be 1k. And this would be kk squared. All right. And it's a symmetric matrix, meaning that the off diagonals, this and this, are the same value. So with covariance, which you may not be familiar with, but that's okay. Covariance, yep, I don't want to get into that. If you don't know what it is, Google it and look it up. I'm not going to make you calculate it, so the computer can do that for us. All right, so then we say the variance of epsilon hat is given by sigma squared times I minus the hat matrix. And the variance of the residual here, for the ith value, is this element sigma squared times 1 minus HII. And remember that I'm doing all this covariance and variance, but what we're saying is we should see sigma squared along the diagonals because we're supposed to have the same variance for all the, so we're supposed to have the homogeneity of, or homoscedasticity, so that we have the same variance for all the values of x. Okay. And so, but HII is the ith diagonal element of the hat matrix. And I won't write out what the hat matrix looks like again because it's really messy, and again, I'm not going to make you use that. I just want you to know there's something called the hat matrix, and it has elements that are related to the variance of the individual elements. And so the estimated variance of epsilon hat is going to be given by MSE times 1 minus this ith diagonal element of the hat matrix. And so we're going to use that as one of our measurements of whether we have an outlier or not. Okay, so there's 4 different types of residuals. Epsilon I hat is the ordinary residual. That's y hat, let's see, yi minus y hat, I believe. Yeah. yi hat. Okay. And then we have the standardized residuals, which is epsilon hat divided by the square root of MSE. So we're standardizing it by the variance, the standard deviation. And so remember that the epsilon is supposed to be a normal 0, 1 distribution. So that means the mean, mu of epsilon, is equal to 0. So this is like a z-score. Okay. So we're taking a z-score because we've subtracted 0, the mean here, and now we're dividing by the standard deviation. So, and z is equal to some value x, or in this case epsilon, minus its mean over its standard deviation. So we're standardizing these residuals so that they have a mean of 0 and a standard deviation of 1, or variance of 1. And this removes the dependence on the unit of the variable. Okay, so that's really not clear. So the variable, okay, because we don't care about the units of the variable. So if we have variables with different units, then by standardizing it, we get rid of that. Okay. Then the studentized residuals, then instead of being just the square root of MSE, we use the 1 minus, we use this estimate of the standard deviation, the square root of that. And so that's what we've done here. And that's to make these, this gives them a constant variance, okay? Because by including this 1 minus HII, any variation due to that observation is taken out by using this measure of the hat matrix. It makes them all the same variance. So it makes it a lot easier to compare these values, okay, when we plot them. Now this is called a jackknife residual, and so what we do is for, this is called R for that, and we take out, this for residual, we take out the ith observation and we calculate this quantity here without that ith observation. And so this removes the influence of that ith observation when we're estimating yi and sigma squared. And so if one of these is very influential or has a big effect, in other words, it's an outlier, then we'll see a big difference when we remove it compared to when we don't, okay, all the others. So how do we detect outliers? So these are the 4 different types of residuals. Now let's talk about the methods that we're going to use to detect the outliers. And the goal of diagnostic analysis are to, 1, identify any recording errors, and 2, to also identify influential observations. Now the recording errors, those are something that you, is very tedious, and you have to say, well, it just can't be this value, or this value doesn't look right. Maybe we typed it in wrong from where we recorded it, or maybe there was something wrong with the equipment, or something, there's something wrong with that the recording of that value. Again, that's kind of hard to find and tedious, but it can be done. So these are what we do with this is not that we can determine whether it's recording error. We will just identify whether it's an influential or possible outlier observation. And these influential observations or outliers will significantly affect either the choice of the variables or the accuracy of the estimates. Okay? So influential observations and outliers are actually a little two different things. Influential points change your estimates, change the model. Outliers could change the model, but they're far away from everybody else. So depending on where in the values of x they occur, that determines how influential they are. So what I mean by that is if I have points here, you can think of this as a lever arm. If I have an extreme point here, it's not going to have nearly effect because it's near the mean of x, nearly the effect that if I had this extreme point way up here has. This point here will be an influential point. Also a point near the bottom, something like one of those, far away from the rest of the data, near one end or the bottom of the range of x or near the top of the range of x. Those are going to be the most influential of points. Okay. But the point in the middle is still an outlier. This would be an outlier, but it might not be an influential point. It might not change much in your analysis compared to a point, say, here. So near the upper range of the x. And again, you can kind of think of it like putting a weight on a seesaw. If you put something near the center, it doesn't affect it nearly as much as something near the end, either end. Okay, so we're going to use these hat matrix leverages, and these are going to be the diagonals of the hat matrix. The book calls them HI because that's one notation, so we're being a little more specific and saying HII to tell you it's the ith row and the ith column, but ith diagonal element is the ith, the diagonal on the ith row and or column, okay, which would be the same. Okay, so it measures the distance of the ith predictor point here, taking all the x's, all the kx variables into consideration from the center, which is the mean of all of those. And remember, this is a hyperplane with k dimensions. And the larger the value of h, the further the point is from the center. But the standardization that's happened here is that, remember, that hi is going to be between 0 and 1. And so we have this where you can, if you're interested, you can look at that, but since we're not going over the matrix part of it, or testing on it, it's not really applicable in this course. So the guideline for the possible outliers is given here. Please write this down on your notes somewhere so you can find this. You'll need all of these together on one sheet of paper, so this will be the hat leverages, and you'll want to record that value. All right, that's it for this video. Don't forget to scan in your lecture notes and upload them to the Google Drive by midnight of the date listed in the course calendar. If you have questions, by all means come to virtual office hours. I am happy to help you. If you can't do that, then you're certainly welcome to email me. But when you email me, I need two things. I need you to email me a picture of your work and a picture of the problem, because I may not have access to the problem. And unlike some people may think, I do not have them all memorized. So I need those two things to be able to help you efficiently. I hope you will take care of yourself, and we hope to see you next time.